Assalamualaikum and a very good day. So in this video, we are going to continue the lesson for chapter 4, which is the final chapter of dynamics course. That is the conservation of linear momentum. In the previous lesson, we have learned about the principle of linear impulse and momentum. So in this lesson, we are going to continue with the conservation of linear momentum. The outcomes of this lesson is for you to be able to understand about the conservative and non-conservative forces. Next is to understand the concept of conservation of linear momentum. And finally, we are going to solve a few related problems using the conservation of linear momentum. So in the previous lesson, we have learned about the principle of linear impulse and momentum. The principle of linear impulse and momentum states that the initial momentum plus the total impulse to move from time 1 to time 2, which is the whole process of the motion, is equal to the final momentum of the object. But in the case where the impulse is equal to 0, so basically this term will not be in the equation, then what we have is the total momentum, initial total momentum is equal to the total final momentum. So this is what is known as the conservation of linear momentum. So basically mv1 is equal to mv2 without the presence of the total impulse. So the conservation of linear momentum in words is the total linear momentum for a system of particles, and it remains constant during the time period t1 until t2. The conservation of linear momentum is often applied when two particles collide or interact. So if you ask when should we use the conservation of linear momentum, it's when you see a problem involving collision of two objects or two particles, then normally we are going to use the conservation of linear momentum to solve the problem. This is because the internal impulses due to the impact cancel out because they are equal but opposite collinear pairs. And another time when the total impulse is equal, it can be neglected, is when the motion is very, very short, and therefore the external impulse multiplied with the very short time to make it the external forces multiplied with the very short time to get the impulse will be very small, and therefore is considered as non-impulsive force. Let's take an example of a hammer pounding a nail. Okay, so basically the situation here is a hammer hitting a nail. So in this case, we can look at this problem as the impact between two particles. The first particle or the first object is the hammer impacting the nail. So let's draw the individual free body diagram. So if we take out the nail and draw the free body diagram, first we're going to have the weight of the nail pointing downwards, and we're going to have a very big force exerted by the hammer on the nail. If we take the hammer now and draw the free body diagram of the hammer, then we're going to have the weight of the hammer pointing down, and as the third Newton's law of motion, reaction equals to reaction. When the hammer applies a force to the nail, then this a similar force but with opposite direction will also be applied to the hammer. So this is the individual free body diagram. if we draw the free body diagram together for both objects during the impact, now we're going to have the weight of the hammer, the weight of the nail, the impact force by the hammer on the nail, and the counter direction of the same impact force being exerted on the hammer itself. So if you can see this forces F is equal force with equal magnitude, but in the opposite direction, and therefore they can be cancelled out because they are actually a pair of forces but in different direction. So the weight of the hammer and the weight of the nail is considered very small as compared to the force being applied by the hammer on the nail. So therefore the weight are considered as non-impulsive force. Okay, so this is an explanation how the conservation of linear momentum is derived. Okay, so to understand better on the conservation of linear momentum, let's look at a few examples. Okay, example number 1. The freight cars A and B have a mass of 20 megagram and 15 megagram respectively. 20 megagram means that it's 20 times 10 to the power of 3 grams. 20 times 10 to the power of 3 kilograms. Okay, and determine the velocity of A after collision if the cars collide and rebound such that B moves to the right with a speed of 2 meters per second. Okay, so what we want to find out is what is the velocity of A after collision. So in this case, there is a collision between these two cars. So let's solve the first part of the question first. First, we define our coordinate system. We take x positive to the right. Weight of both cars are non-impulsive as compared to the larger force exerted by both cars due to the impact. So the weight can be considered as non-impulsive. And if you notice also in the problem, it doesn't state the time, which shows that the impact might occur in a very, very short time. So the momentum is conserved. Therefore, sum or total momentum initially m1 v1 is equal to the sum of m2 v2. So we will apply the conservation of linear momentum, that is ma va1 plus mb vb1. Remember, now we have two objects, so you're going to have to write both mv for both cars. So here is ma va1 for car A plus mb vb1 for car B is equal to ma va2 plus mb vb2. What we want to find here is what is va2, because vb2 is given after the impact. Vb is equal to 2 meters per second as stated here. So on the left hand side, we have 20 megagrams, which is 20 times 10 to the power of 3 kilograms, multiplied with the velocity of A, that is 3 meters per second to the right. So it's going to be positive 3 plus 15 megagrams, 15 times 10 to the power of 3. And it is moving 1.5 meters per second to the left. So it becomes negative here. On the right hand side, we have 20 megagrams times VA2. This is the one that we want to find. And 15 megagrams times 2, which is given here. That is the velocity or the speed of B after the collision. So from here, straight away, we will get the velocity of car A, VA2 is equal to 0.375 meter per second after the impact. Okay, now we move on to the next part of the question. If A and B are in contact for 0.5 seconds, find the average impulsive force which acts between them. So this part of the question is no longer conservation of linear momentum because the time is given here. So to solve this, we need to apply the principle of linear impulse and momentum, the one that we learned in the previous lesson. So we choose only one car for the calculation because remember, when two objects collide, the force applied, the same force will be applied to both objects. But the difference is that one object will, the same magnitude of force will be applied, but in the opposite direction. So if we choose car A, then we're going to take positive to the right in x-axis. This is the equation for the principle of linear impulse and momentum, MAVA1 plus the total impulse in x-axis for the time from 0 to 0.5 is equal to MAVA2. So 20 megagrams times 3 meter per second. This is the initial velocity of car A, plus the average force multiplied with the time 0.5, this is the impulse, equals to the 20 megagrams times 0.375. This is the velocity of car A that we have calculated in the previous part of the question. So from here we get the average force acting on car A is minus 105,000 Newton. Okay, so if you go ahead and calculate for car B, do the same thing, you will get F average is equal to positive 105,000 Newton. So this shows, this proof that the action and reaction occurs during the impact and the same force but in the opposite direction is applied on both objects. Okay, so that is for example problem number 1. Let's look at example problem number 2. 5 kg block A has an initial speed of 5 meter per second as it slides down the smooth ramp. So, okay, smooth here means that there is no friction that we need to consider throughout the motion here. After which it collides with stationary block B of mass 8 kg. So block B initially is not moving. Block A is traveling down and it impacts block B. So you notice here there is an impact between two particles, two objects. Then we have to apply the conservation of linear momentum here. If the two blocks couple together after collision, so in this case they are not, there is no rebound occur. So A will impact B and then they are going to start to move together. Okay, so this is the difference between this problem and the previous problem. So determine their common velocity immediately after collision. Okay, so what we want to find out is the collision between A and B down here. So definitely we know we need to use the conservation of linear momentum, which states that MAVA2, the VA1 is 5 meter per second, so we need to know what is VA2 here for A to impact B plus MB VB2. And if you notice, VB2 is equal to 0 because block B is initially not moving, so this part is basically equals to 0, is equal to MA plus MB because they are moving together. So now we have to sum the mass of both blocks and multiply it with V3. So this will be their final momentum. But the question is, what is VA2 here? We don't know what is VA2, the velocity of A before it impacts B. Definitely it is not equal to 5 meter per second because throughout the motion there must be some losses to surroundings, and VA2 must be different than what it has initially of 5 meter per second. So how do we determine what is VA2 here? We see that there is a change of height going down here. So velocity of A just before impacting B, VA2, can be determined using the conservation of energy. This goes back to chapter 3. Okay, I just want to remind you that the impulse and momentum chapter usually will involve also what we have learned in chapter 3, that is work and energy. So you have to most of the time you have to use both knowledge from both chapters. So to calculate this, we will set this bottom line here as the datum. Okay, so this will be the datum. So basically block A will travel from 1.5 meter above the datum going down and impacts B. So the conservation of energy states that T1 plus V1 equals T2 plus V2. In this case, there is no spring involved, so V1 here will only involve the gravitational potential energy and not elastic potential energy. T1 is 1/2 times the mass of block A, which is 5 kg, multiplied with its initial velocity, which is 5, so 5 square here. V1 will be W times G, so 5 times 9.81 times 1.5. This is sorry, not W times G, my bad, it's W times delta Y. So delta Y here is 1.5 meters, so 5 times 9.81 times 1.5 equals to 1/2 times 5 times VA2 square. This is the one that we want to find, and V2 at the datum is definitely equals to 0, so V2 is 0. So from here you will get VA2 is 7.378. So obviously you know that starting from 5 meter per second moving down, since there is no friction involved, so point A is gaining speed. It increases the speed before it impacts block B. Okay, so now let's continue with the conservation of linear momentum, which is this equation that we have written before, and now we have VA2 to get what is the value of V3, what is the velocity of block A and B together after the impact. So from here we have 5 times VA2, 7.378, plus 8 MB, the mass of block B, and initially block B is not moving, so it will be multiplied with 0, equals to 5 plus 8, this is the mass of both blocks, multiplied with V3, this is the velocity that we want to find. So in the end, we will get the velocity of both blocks after the impact moving together. V3 is equal to 2.838 meter per second. Okay, one final example, example number 3. Block A and B have a mass of 15 kg and 10 kg respectively. A is stationary, initially not moving. B is having a velocity of 15 meter per second, moving to the left and impacting block A. Okay, just before and the block couples together after impact. So basically after the impact, like the previous example number 2, both blocks will stick together and forcing the spring to be compressed. So what we want to find here, what is the maximum compression of the spring? Okay, so definitely this is another impact problem of two objects or two particles, so we need to use the conservation of linear impulse and momentum. MA VA1 plus MB VB1 equals to MA plus MB times V2, because after the impact both blocks will stick together. So we have here VA is equal to 0. It is stationary. 15 times 0 equals to 0, plus block B 10 kg times 15 meter per second. So now we're going to set positive to the left, is equal to 15 plus 10 V2. So from here we get V2 6 meter per second to the left. Okay, I forgot to draw the direction of positive, the positive direction here. So basically we will follow the motion of B that is positive moving to the left. Okay, how do we determine the maximum compression of the spring? Maximum compression now involves the change of displacement. So when we talk about displacement, remember we need to go back to the work and energy chapter, and therefore to determine the maximum spring compression we need to use the conservation of energy. Again, T1 plus V1 equals T2 plus V2, and there is no change in change of height here. Therefore, the gravitational potential energy is equal to 0, but what we have here is the elastic potential energy, which is half Ks squared. So T1 for both blocks. Now we are talking about both blocks. They are going to stick together. Okay, so 1 over 2 m is now the total mass of A and B, 15 plus 10 times the velocity that we have just calculated, which is 6 squared. And initially, just before immediately after the impact, the spring has not been compressed yet. So V1, the initial elastic potential energy, is equal to 0 because there is no S, no compression yet. S equals to 0. So half Ks squared, S equals to 0, V1 will be equal to 0. But then what we are interested in is V2. When the spring is fully compressed to the maximum, the block will stop moving. Therefore, T2 is now equal to 0. Okay, T2 equals to 0 because there is no more kinetic energy. So if you imagine both blocks coupled together, start moving to the left, and when it reach the maximum compression of the spring, the block will stop moving. So when it stops moving, the kinetic energy will be equal to 0. The elastic potential energy V2 is then half K. K is 10 kilonewton, so 10,000, multiply with S square, S max square. This is the maximum compression of the spring that we want to calculate. So solving this equation here, then we will get S max is equal to 0.3 meter. Okay, so again, what I'm showing you here, that you have to use the conservation of linear impulse and momentum to find the velocity, and most of the time the question in this particular chapter will also involve the use of knowledge from chapter 3, that is work and energy. So you might want to familiarize yourself with both methods. From chapter 3 and chapter 4, that is work and energy, as well as impulse and momentum. So in summary, we have learned in this video about the conservative and non-conservative forces. Okay, non-conservative forces is when you can neglect the impulse for that particular force, maybe due to the short time of the motion, or maybe it is small as compared to the internal impulsive force. The concept, we have also learned about the concept of conservation of linear momentum, and finally we have solved related problems using the conservation of linear momentum. Okay, therefore this is the end of this lesson. I'm going to upload the next video where I will explain about the impact, which will also use the concept of conservation of linear momentum. Until then, thank you, and I'll be seeing you in the next video.